Welcome to today's explainer. If you look closely at the world around you, from the screen you're staring at right now, to the water in your glass, to the actual DNA inside your cells, it's all the result of this incredibly intense microscopic drama. And it's a drama that's literally been playing out since the dawn of the universe. We're talking about atoms constantly bumping into each other, interacting, and really just desperately trying to find some stability. So let's dive right into this invisible world. Today we're going to explore exactly how these tiny building blocks stick together. Specifically, we'll be zeroing in on the core differences between the two main types of chemical relationships, ionic and covalent bonds. We're even going to see how these invisible bonds completely dictate things like melting and boiling points in the real world. It's going to be a fun ride. Here's our quick roadmap for today. We're hitting the quest for stability, ionic versus covalent bonds, the boiling point battle, weak intermolecular forces, and we'll wrap it all up with carbon, the versatile element. All right, part one, the quest for stability. Because honestly, before we can even talk about how atoms bond, we need to ask why they even bother in the first place, right? So, how exactly do atoms achieve this ultimate stability? Well, in chemistry, stability basically means having a totally full outermost electron shell. We call this the noble gas configuration. You can think of the noble gases, like helium and neon, as the cool, completely unbothered kids of the periodic table. Their outer shells are already full, so they're perfectly stable and almost completely unreactive. They are the absolute ideal that every other element is just trying to mimic. Everyone else on the periodic table, they're restless. Their outer shells are half empty, so to find that subatomic piece, they have to interact. They have to bond. And that brings us to the first really brilliant solution to this problem, covalent bonding. This is all about the mutual sharing of electrons between atoms so they can both hit that dreamy noble gas configuration. It's completely cooperative. Instead of fighting over electrons, these atoms figure out that by just overlapping their outer shells, they can both count the shared electrons as their own. So those shared electrons essentially exist in the outermost shells of both atoms at the exact same time. It's the ultimate microscopic compromise. Moving on to part two, ionic versus covalent bonds. Let's pit the sharing method directly against the alternative. Okay, so let's look at the core differences in action here. On the left, we've got ionic bonds, which involve a complete transfer of electrons. One atom outright loses an electron, and the other absolutely snatches it up. Now, because electrons have a negative charge, this outright theft creates highly charged particles called ions, one positive, one negative, and boom, they stick together like super strong magnets. But check out the covalent bond on the right. This is an equitable partnership. Because they're peacefully sharing their valence electrons, nobody is gaining or losing a full charge. They stay totally neutral. No highly charged particles at all. So, the big takeaway? Ionic is all about complete transfer and charged ions, while covalent is all about mutual sharing and neutral molecules. Think of it like a blanket. An ionic bond is one person completely hogging the blanket, while a covalent bond is two people perfectly sharing it. And it's super cool to see how this sharing scales up based on what the atoms actually need. On the left, you've got a single bond in a basic hydrogen molecule. Each hydrogen atom brings one electron to the table, but they need two to be stable. So they just share one pair. We draw that as a single line connecting the H's. But sometimes atoms are a bit more needy. Look at the oxygen molecule on the right. Oxygen atoms need two whole electrons to find stability, so they share two pairs of electrons, creating a double covalent bond. It's just a perfectly elegant mathematical fix to their instability. And get this, they can actually take it even further. Nitrogen needs 3 electrons to fill its shell, so what happens? 2 nitrogen atoms link up and share an incredible 3 pairs of electrons. That is literally 6 electrons spinning furiously between them just to keep that N2 gas together. So, depending on what they need, covalent bonds let atoms build single, double, or even triple links. Section 3. The boiling point battle. Okay, so we've got the theory down, but how do these tiny invisible bonds actually change the stuff we can touch and feel? Let's look at some real-world data to compare melting and boiling points, because this is where the differences really pop. Here we have 4 common carbon-based covalent compounds: acetic acid, chloroform, ethanol, and methane. Check out those melting and boiling points, measured in Kelvin. To put that in perspective, a comfortable room temperature is about 293 Kelvin. So ethanol, the stuff in alcoholic drinks, boils at just 351 Kelvin. Chloroform boils at 334. Now, if you think back to ionic compounds like regular table salt, Those things need massive, insane amounts of heat to break down. We're talking well over 1,000 Kelvin just to melt them. But these covalently bonded carbon compounds, they melt and boil at surprisingly low temperatures. They turn into gases super easily. So what's causing this massive disparity? To really drive this point home, let's just look at methane. Methane boils at an astoundingly low 111 Kelvin. That is roughly negative 162 degrees Celsius. So it is absolutely freezing. Yet for methane, that's enough heat to literally boil it into a gas. This shocking contrast perfectly highlights the core physical difference we're focusing on today. Ionic compounds are these rock-solid, high-heat structures, while covalent molecules are perfectly happy hanging out as liquids or gases at everyday temperatures. Part 4. Weak intermolecular forces. So this brings up a huge paradox. If covalent bonds are so strong, why does it take almost zero heat to boil something like methane? Well, the secret lies in a really important distinction. The covalent bonds inside the molecule are incredibly strong. The connection locking the carbon to the hydrogen in methane, it's like superglue. However, the forces pulling the separate methane molecules toward each other, which we call intermolecular forces, are actually super weak. So when you boil water or methane, you're not physically ripping the atoms apart. You're just giving the molecules enough energy to float away from their neighbors. Since those neighborly attractions are so weak in covalent compounds, they have super low melting and boiling points. It's the exact opposite of ionic compounds, which lock together in this massive, tightly gripped crystal grid where every ion pulls fiercely on its neighbor. Oh, and there is one more massive side effect to this lack of charge. No charged particles means absolutely no electricity. Because covalent bonding is all about sharing electrons rather than transferring them to make ions, these molecules are generally terrible conductors of electricity. For an electrical current to flow, you have to have moving charges. If you dissolve an ionic compound in water, you get this charged soup of moving ions that conducts electricity beautifully. But if you dissolve a covalent compound like regular sugar into water, you just get neutral sugar molecules floating around. No charge, no current. Simple as that. Finally, Section 5, carbon, the versatile element. Now that we know the rules, let's look at the absolute master of the covalent bond. Carbon is without a doubt the undisputed king of covalent bonding, and its incredible versatility comes down to two unique traits: tetravalency and catenation. Let's break those down. Tetravalency just means carbon has 4 valence electrons in its outer shell. It needs 4 more to be stable. This effectively turns a single carbon atom into a 4-way intersection. It can bond with up to 4 other atoms, like oxygen, hydrogen, nitrogen, all at the exact same time. It's the ultimate team player. And that leads right into carbon's second superpower, catenation. Catenation is just a fancy word for an element's ability to form stable bonds with itself. Look at the sheer variety of structures carbon can build. It doesn't just link up once or twice. It can build long, straight chains, wildly complex branch chains, and even these beautiful little closed molecular rings. Almost no other element can do this without the whole structure just collapsing. These endless architectural possibilities are exactly why carbon is the foundation for the millions of organic compounds in our universe. Which brings us to the end of today's explainer. But before we go, I want to leave you with a thought to chew on. If carbon didn't have this incredibly precise ability to peacefully share electrons through covalent bonds and to link up with itself in all these infinite patterns, would the immense complexity of life as we know it even exist? Every single protein, every strand of DNA, every living cell relies on this delicate, low boiling point, non-conductive framework of covalent bonds. It really goes to show how the simple, invisible act of sharing electrons is what makes our beautiful, complex, visible world possible. Thanks so much for joining me today, and keep exploring.